Okay, so let's do a hard problem. This is a step shaft, and it's got a 32-pound gear sitting right here, and I want to calculate the natural frequency. We're given the Rayleigh expression that the first natural frequency is approximated as the square root of g times this two sums, right? So this is this weight or times the deflection due to just gravity divided by the sum of the weights times the deflection squared. And those y's are just gravitational deflections. Okay. So this W1 here is essentially just the weight of that part of the shaft, and this W2 is essentially just the weight of that part of the shaft, and then I've got that 32-pound gear. So I need to find the deflection due to those loads. Okay, I've set up the problem where I've got gamma for steel. If you look up, this is the gamma is the specific weight. If you look this up on Google, it's about 0.28 pounds per cubic inch. This is 30 million psi for Young's modulus. This is the acceleration of gravity in inches per second squared. So there's have to multiply feet per second squared times 12. Okay, here's the lengths of the two parts of the shaft, the diameters of the two parts of the shaft, the resulting areas. That's just pi d squared over 4. Here's the weights. That's just gamma AL for each chunk, and there's the force. Looks like I've done this problem before, and so I need to get these. So here's my unknown constants for my integrals, and I'm just going to set them all up as just 1 for right now. Okay, so there's my problem. Doing this by hand, I just have the three forces right there in my distributed load. So I've got W1 acting at L1 over 2, that's 5 inches in, right? There's the force acting at 10 inches in, and then the W2 there acting at 14 inches in, it looks like. Okay, I'm doing this integral by hand, just writing this down on a piece of paper or something. So here's the shear force. If you remember how to integrate these things, the negative ones all bumped up to zeros. That's the only difference, and then we're adding an unknown constant C1. Okay, I've further given these names. So this gamma, this field right here has the name gamma. This cell has the name E underscore E. I don't know why I didn't do an underscore gamma. I've got underscore everything else. If I have a number like L1, then it thinks it's our column L row 1, so you have to put the underscore to make sure that it's just the variable L1 like that. So I've got all these things set up as C1, C2, C3, and C4. And then I've got these columns. So I'm going to do X going from 0 to 18 inches by some small step. Here's the shear force, which is just going to be translating this equation into Excel, and then I'm going to start numerical integrations to get the bending moment. Here's the diameter and moment of inertia. This is m over EI, this cell right here. So when I do the slope, it's just going to be the integral of that column right there, where I is actually going to be inside the integral sign when we do this. Okay, and then one more integral gets me Y. Okay, I'm going to start out in a negative territory here because we're going to toast a data point to get our first integral here. Kind of like this. Let me show you. If I've got axes X and Y like this, and I'm drawn with my mouse so I look spastic here, but that's okay. And I've got a curve like this for which I know data points, say here and there and there and there. My trapezoid law or rule for integration is I'm going to find the area of this right here, pretending that's a straight line in between. That's my first trapezoid. Here's my second trapezoid, and here's my third trapezoid. So even though I've got 4 data points, 1, 2, 3, 4, I'm only going to get 3 areas. So I'm toasting a data point by doing an integral. So I'm going to start my beam in slightly negative territory here. I'm going to go by steps of 0.1, so this is going to be minus 0.1. This will be 0. And then I'm going to copy that down until I hit 18 inches. Like that. Okay. Here I'm just going to, in fact, you know what I'm going to do here? I'm going to call this whole thing X, so I don't have to keep typing weird things. So I'm going to just highlight every cell there, and I'm just going to call that whole thing X, like that, and hit enter. So individual ones aren't X, but the whole column is X. But it makes it so that I can actually use X in my formulas now. So now the shear force is equal to, and I'm just going to type this in Excel. So that's W1, which is sitting right here, times, and this angle bracket is just an if statement. So if, and I can just literally type X now because that's that whole column over there, right? If X is less than L1 over 2, so L1 is right here, divided by 2, then it's 0, otherwise it's 1, and there's my first if statement, or my first angle bracket right there. Notice I'm not doing negative here because I'm going to put all this in a square root. If there's a negative number inside that square root, we're going to have problems, so I'm just pretending all those are positives. So I got that first term, now I go plus F, and F is right here, times, and I got another if statement, if X is less than L1, which is just right here, then it's 0, otherwise it's 1, plus W2, which is right here, times if X is less than L1 plus L2 over 2, so this is L1 plus L2 divided by 2, then it's 0, otherwise it's 1, like that. And then I have to say plus C1, which is right here. So there is my, this formula translated into Excel right there. Okay, I'm going to get this to the black cross piece and then just double click so it copies it all the way down. So I did that integral by hand and then just translated this formula into Excel. Next one I'm going to actually do with Excel. So the bending moment is the integral of this plus another constant C2. So I'm going to say this is equal to, and the integral we're doing with the trapezoid rule. So we're going to find the value of this guy and add it to the value of that guy and find like an average height. So the average height times the width. That rectangle has the same area as the trapezoid does, because this corner fits into that corner right there. So this is equal to, oh, I'm not doing the integral yet. This is just equal to C2. Sorry about that. Now this next one is going to be equal to the previous result plus the area of that trapezoid. So the area of the trapezoid is this guy plus that guy divided by 2. That's the average height times the width, which is that guy, the x direction, minus that other x coordinate there, like that. Whoops, I got an extra minus sign there. So again, this one is just C2, and this one is the previous cell, previous result, plus the average height times the width of the trapezoid. And then I can just copy that one down like that. So at any random place here, it's going to be the result from the previous cell plus the area of that trapezoid. And we just kind of tack it on as we go. Okay, here's the diameter. This is just equal to if x is less than L1, then it's D1, otherwise it's D2. And I is just equal to pi over 64 times the diameter to the 4th. So I can take both of these guys now and carry them on down. So it switches right here at 10 inches, right? M over EI is just going to be equal to M divided by E divided by I, like that. Click that down. And now we're ready to do the next integral on M over EI right there. So again, we're going to, let's see, this one was C1, this one's C2, so this one will be C3. So this is equal to C3. And then here's my, this will be equal to the previous result plus the area of the trapezoid. So again, this is the average height. That's going to be this plus this divided by 2 times the average, or excuse me, by the width, which is going to be that minus that, like that. Again, we're just doing the average height times the width, right? And what we're integrating is m over EI there. So double click there. This one's going to be equal to C4. And then the next, the integral here is going to be equal to the previous result plus the area of that trapezoid. So this is going to be the average height of this and that times the width, which is this minus that, like that. Double click that all the way down. Now these are just fake numbers right here, so we have to take care of those using the solver. Okay, so I'm going to launch the solver, and it looks like I've already. Usually when you do this, there's nothing here or there, but there is a cell here, like say K, 25 or something like that, right? So when you open up the solver, you want to get rid of this thing, because I don't want to do a single objective. I want multiple boundary conditions, so I'm going to do those as constraints down here. But I do want to change these 4 right here. Those are the guys I'm going to dial in. And now I'm going to add my 4 boundary conditions. Well, for this beam right here, I just have no deflection or moment at each end, so there's my 4 boundary conditions. So I'm going to add one here and say that the, let's see, the moment here is, there's x equals 0, moment is right there. So I want that to be equal to 0. And I'm going to add another one where the deflection, again, at x equals 0 is the second row, right? So this equals 0. So my bending moment and my deflection are 0 at x equals 0. And bending moment and deflection at the other end. So I'm going to have to scroll all the way down to the other end of the beam. This column is the bending moment, so this equals 0, and that equals, 0. So there's my boundary conditions. So I have C24 and C204. 24 is this guy, and 204 is the end of the beam, right there. And H24 and 204 as well, where H was the deflection there. So that should be it. Solve. It has found a solution. Notice that the deflection here is, the bending moment there is close to 0, and the deflection is also close to 0. At the other end, also close to 0 in both places. So for instance, I could, if I wanted to, plot the deflection. So if I highlight all of the x values and then discontiguously select also all the y values here, then I could insert a scatter plot of the deflection like that. And notice we're not deflecting very much. That's like there's 1/1000th of an inch right there, but again, that's not much weight on such a beefy shaft. And that is, again, just the deflection only due to the gravitational loads, the weight of the shaft itself, and then the gear that's sitting on top of it, like that. But it is the deflection that I need to do my little formula here. So let's do it. This will now be equal to the square root of g, which is right here, that one, times, and now I've got some, the sum of the wi. So I need the weight of, let's see, the first chunk is w1, times the deflection there, and that's at 5 inches, in the middle of that 10-inch segment. So 5 inches is right here, and the deflection at 5 inches is right there, right? Plus, the next force is this F thing right there times the deflection there, and that is at 10 inches. So I'm going to scroll down to 10 inches here and get the deflection there, plus the weight of the last thing is W2 times its deflection, and it's happening at 10 plus half of 8 is 14 inches. So scrolling down to 14, deflection at 14 inches is right there, and then I'm closing the parentheses there, and I'm dividing that by, I'm going to copy this and divide by the same thing, and I better close my square root parentheses too, except I actually want to square those guys now. So we're squaring all the deflections, so this is squared and this is squared and this is squared, like that. So I got square root of g times the sum of wi yi divided by wi yi squared, and it looks like it's 2200 radians per second. If I want to get that into RPM, I have to say that's equal to this times 60 divided by 2 pi. So that's about 21,000 RPM, which is pretty fast, but again, that's a pretty light shaft for such a beef. I mean, it's, not much load's being applied to. So it's pretty big in diameter for its length. So 20,000 RPM is my first critical speed, and that's it.